Okay. Thank you, Marwan. We'll see, talk about what kind of rocks you might collect is the main thing I want to do tonight. So what I'm going to do, hang on. I'll start sharing my screen for stuff. I'm going to try this one. Okay, so I'm hoping you all are seeing a picture that says collecting rocks. Does it look good?
Yes, we're good.
Okay, that's good. So here's the main deal is watch for rock. Okay, sometimes this is a sign, real sign in Idaho, and they probably meant falling rock, but hey, you can watch for rock all the time. Just don't drive off the road while you're doing it. Also, it's kind of an interesting example of how to save money on signs. Make one go for the next 60 miles. But hey, I can beat that. Okay, you should always watch for rock. Oh, get it going. Oh, hang on. There it goes. Should always watch for rock. Okay, you never know when you might find some interesting ones. In fact, you go out on a trail somewhere, if you kind of begin to understand how rocks form and how they get put together, it's almost as though there's a posted note on the rock that says "My story," because you can interpret how it was made. You look at the one across the trail, well, it may tell you even a little more, it may tell you much of the same thing. Go down the trail, get another rock, you got a new story, and beyond that, another one. So it's in walking in the woods can be a little bit like walking through a library. Okay, walk down the aisle, pull out a story that you like, and see what you got. So it's kind of fun to see, go out in nature and get the story of what's been there and what's there now. So as I start this, what I want to say is a little bit of a disclaimer. When you're out collecting rocks, we need to be sure you please collect them in places where it's right to do. Okay, often we see our rocks in local, state, and national parks, but that's not the place to collect them, please. Another one in our area is Baltimore's watershed properties. They want you to leave stuff there. So please keep that in mind as you go. And even though this is Collect Rocks Day and a lot of folks have a rock collection, the other way is you can collect pictures of rocks. You can do that anywhere, okay? And obviously tonight I'm going to be showing you pictures. Pictures don't work real well on Zoom anyway, or I'm sorry, real rocks don't, but pictures do okay. So we'll see pictures. Besides, they're a lot easy to carry, and some people already said they are filled up their basement. So pictures are a good way to go. Also, you'll all probably know, don't collect on private property without permission, of course, and always think about safety when you're out there. Don't be climbing the cliffs and falling off or standing too close to the road. So all I want to do is start with, do it the right way. Don't get hurt, don't get in trouble. Okay, so what we're gonna do is talk about what rocks might you look for and what might you notice about them if you're out there making a collection. We probably have to start with being sure everybody's clear on terminology. You remember from chemistry class that elements are the basic building blocks of nature. They combine to make minerals, okay? So minerals are naturally occurring solids. They have a formula. Briefly, you can just think of as naturally occurring chemical compounds. And then it's minerals that get together to combine to make rocks, okay? So rocks are just a natural aggregate of one or more minerals, okay? This helps to keep track of what's a mineral and what's a rock. And in the chat already, some people have talked about both of those. We'll see how the minerals go together and make rocks. If you're going to identify rocks, it turns out there's two things that you look at primarily. What are the minerals, the mineral composition, and the other piece is texture. How do they go together? Well, let me talk about each one of those. Composition is the first part, and turns out most of the rocks at the surface of the earth are silicates. Hang on, I'm moving a menu here. Silicates have contained silicon and oxygen, and that's like 90% of the rocks of the crust of the earth. The silicates are divided into two groups. One is the felsics, okay, which has quartz, which some people have mentioned, potassium feldspar, sodium plagioclase, and muscovite mica. Okay, these are in the pictures here, and you've probably seen most of these. The main point is what you notice is they're mostly light colored. Potassium feldspar is often pink, but still light in general. And that's the felsics. Okay. The other part of the silicates is the mafics. Okay. They are amphibole, pyroxene, calcium plagioclase, olivine, a nice green when it gets its name from being the color of olives, and biotite mica, the black mica. Point is, all of these are dark colored. And so one way on the mineral composition for rocks, especially igneous and metamorphic rocks, is you can, the color will begin to give you a sense of what's its composition. Is it mostly felsic or is it mostly mafic? Okay. When we do sedimentary rocks, a lot of these mafic ones will have worn away and kind of disappeared, but this works, the colors will give you a start on the mineral composition for at least some rocks. Now starts on that part. Then the other one, there are really thousands more minerals, and a lot of them are silicates and some of them are non-silicates. A common non-silicate is calcite as a mineral. It's calcium carbonate. It's usually light colored, and especially if you take a nail or a knife, you can usually scratch it fairly easily, usually more easily than the silicates. So that's another one that's pretty common, and we'll see where it shows up in the rocks as we go. Another way to identify calcite that you may know about is it also effervesces in acid. Okay, so if you carried some like hydrochloric acid or even vinegar, it will also sometimes effervesce depending on its exact composition. And that's a way that geologists figure out that they have calcite. So there's some real quick things about minerals. There's that 5,000 or more of them, so we can't spend all night on that, but it'll give you an idea of what we're going to look for in composition. The next part is you pick up a rock, you start looking at the texture, and there's several different textures we can talk about. Here's one, coarse versus fine grained. You can ask yourself, can you put a pencil on separate grains, or is it really hard to tell the difference between them? So for example, you can see the pink feldspar on this one, which is separate from the dark mafic one over here, and each of the colors you can see separately. The one on the right, however, is almost uniform black. There's a few little white spots, but some of that's just from the picture. And so it's hard to put any kind of spot for a separate grain. So the one on the left is coarse, the one on the right is fine grain, something you can look at right away when you pick up a rock. Another texture can be, does it have layers or not? And as it says, this can mean minerals in layers, or it could break in layers. So here's one that clearly breaks in layers in sort of two ways. In the whole stack here, we have some that are solid and some that are falling apart. That's layers. But also within the, especially within the ones falling apart, you can see lots and lots of layers in that rock. Or here's one that's also layered, but it has its minerals in layers instead of breaking apart in layers, white to black to white and so on. And the whole point is this contrasts with a rock like this one, which does not have layers. So it's something when you pick up a rock, you can start looking for that texture. Does it have layers or not? Okay, and they come in different forms, and we'll see. The third kind of texture is it clastic or is it crystalline? Clastic means it comes in pieces of some sort. And the way you can, an analogy for this one is if you had a bunch of frozen peas, they'd all be little pieces, but then you put them in sauce and now they're all kind of combined. Okay, that's different from rock candy, which is a solid chunk of different crystals of sugar. So our rock example, as you can see, this one is clastic on the left, and it's got lots of little pebbles in it and eventually sand-sized pieces, and they've all been glued together into sort of a matrix, but they were originally pieces. While the one on the right, which is a piece of granite, the crystals all grew in it at the same time till they met up against each other. So they never were separate pieces. They were all just forming together till they've created the entire rock of one crystal next to another, and so on. That's a crystalline rock. So when we pick up rocks and we start collecting, we say, okay, those are the kind of things to look for, is what are we seeing of those textures? So if you're going to go out and collect, it can help to know what are you going to find in different places if you may want to set out to look for certain things. In Maryland, it helps to know the overall geography. And then the question is, how can you know that? Okay, well, what we're going to do is I'm going to use a web map that I created, but you'll also get a link for this map, and you will be able to use it in much the same way that I'm using it. So what I'm going to do is switch to, let's go here, and let me go here. Okay, now I think you're seeing a web map, which is Maryland Geology for Education. Does that look okay? Are we getting that? Yeah, okay, that's good.
Yeah,
Okay.
we're good.
All right, that's good. When you start it, okay, don't try to copy down the huge URL because it's a bother. There's a much shorter one you'll get in the chat. When you start it, it'll look like this. You'll get a map of Maryland, and it'll look kind of blank on the left. That's because when it starts, it defaults to the legend, but there's no layers turned on, so there's no legend to show. So the trick, and this is part of the note in the chat, will be you click on this content button up on the upper left, okay, and then you see a whole list of possible layers to turn on. Well, okay, I'm going to go down to the bottom since we're looking at geography here, and I'm going to turn on one called Maryland Elevations. It shows the elevations of Maryland in different colors, from low down here in light green to getting darker green, then orange, then red is getting higher, some more red, and finally the brown and the gray out here is the highest. And so we see the whole range of elevation, good old Maryland, mountains to the sea. Okay, we got lots of different topography. Well, if you try to divide up the topography so it kind of goes together, you're dividing them into what's called physiographic provinces. These are the red outlined areas where everything inside one particular one is a similar topography. And this kind of helps us organize where we are in Maryland. On the web map, you can always click on something and it will give you some information about whatever layer is on. So this is the coastal plain. This is the Piedmont. This is the Blue Ridge. Right? This is the Valley and Ridge, or Ridge and Valley, gets both names. And this is the Allegheny Plateau out here. There are our main physiographic provinces. And we're going to find out, oh, if you go to different ones, you'll find different kinds of rocks. I'm going to switch back to here. This is a little reminder. Remember the content button when you need it. Okay, here's our provinces. Here's the names on them. You may be familiar with these already. And it's nice, kind of worth knowing these, because what we're going to find is that if we look at Maryland, it ends up being kind of a cross section of the provinces that go all up and down much of the East Coast. I'll switch back to this map. And what I'll do is we were looking, I have the Maryland physiographic provinces on. I'm going to change the base map because it's going to show up some lines better. I'm going to change it to topographic. This is something you can do. This map will let you choose any of these kinds of map as your base map. And if I turn on the US physiographic provinces, then also up here's a bookmark. Several bookmarks exist there, and I can zoom it out to the Appalachians. And what you're beginning to see is the 5 provinces that we found in Maryland are just a cross section of 5 provinces that run all the way up and down the East Coast. So once you learn what's going on in Maryland, you have an idea of what's going on all the way down into all these other areas. Makes Maryland a great place to learn about geology. So those layers are available on the map. And so here they are labeled. You can see they continue on. So we have the provinces. That helps us organize what rocks will we find where. And so now that's the question. What rocks make up the provinces? To find that out, we need to look at geologic maps. In geologic maps, the rock units are called formations. And a really common format is a name that's put together with the name of a place, which is where it was first studied, and a rock type. So some examples: the Baltimore gneiss, the Catoctin metabasalt, the Antietam sandstone, the Wills Creek shale, all those have a place name and then a rock type. And that's normal for most formations. Okay. So if we go back to our web map and see, okay, let's do geology. I'm going to turn off that and the elevations. Okay, and we're going to zoom back into Maryland. And so this map has the geology in several different layers. There's one for Western Maryland, which is just Western Maryland, that they put together in 2013. If we want to look at the whole state, what we have is 5 different sections from the 1968 map. So we have Western Maryland, the Piedmont, Southern Maryland, the upper eastern shore and the lower eastern shore to get the whole state. And I expect it may take a little time for this to zoom its way out, depending on your connection, but hopefully it'll get there. And I hope everybody's seeing a very colorful map of Maryland. It makes a great even piece of art because it's really pretty. And what you notice is, wow, the patterns are different down here in southern Maryland than they are here in the Piedmont, and then they're different again out in the west. So all of these are the different formations in Maryland, and you can zoom in. You can use this to find where you're going to collect rocks, but you can also probably want to start with what's under your house. Okay, so use the map to figure that out once you have time. And if you click on any of these when they're on, I'll click on this one, and then I'm going to make it full screen, making it a little easier to read. I clicked on the Conococheague limestone formation. It tells me about this rock. It tells me it's sedimentary. It tells me it's mostly limestone, but also has some shale and dolomite in it. Tells me its age, something about where it is, how thick it is. Tells me if it has fossils or not. For those of you who are interested in that, we're not going to do much with fossils tonight. That's another talk from somebody else, but okay. It does tell you where you might find some. And then there's some items about what does it do with topography and how was it formed? What was going on when it was formed with plate tectonics and things. So you can click on any of these. Hang on, I'm going to do something up here. There we go. You can click on any of these and it'll give you that same information. That's what it's designed to do. Okay. Now, a problem with this, you might say, is that it's almost a little too complicated. That was our GIS map. There's so many colors, it can be hard to figure out what's going on where. Okay, so it'll help if we start generalizing these to rock types to really rock classes. Those are things you probably remember from school. The groupings separated by their origin, which are igneous, sedimentary, and metamorphic rocks. This will let us kind of condense the information instead of it all being a big mess together. And what this is really talking about is the rock cycle. You may remember that from school too. Basically, since it's a cycle, we can start anywhere, but if we start with igneous rocks, they're the ones that melt and then cool to form a solid rock. They may cool underground, they'll be intrusive. They may cool above the ground as a volcano, that would be extrusive. But in any case, eventually they start being broken down by the weather. So weathering breaks them down into smaller pieces. They get transported and deposited and become a bunch of sediments. They become lithified. That means turn them into solid rocks, in which case they'll make sedimentary rocks. If the sedimentary rocks get buried more or they get squeezed by plate tectonics, they'll get more heat and pressure, and that would turn them into metamorphic rocks. They've changed into a new form. And if the heat keeps on going, they would melt and they'd end up being igneous rocks, and we've made it all the way around the cycle. Okay, so those are our three main classes and where they come from. Let's talk about those and where they occur in Maryland. Okay, that's one map. Let me go back to the real map. I'm going to turn off the specific geology that's here and say, okay, can we simplify this to just rock classes? Okay, well, that's that layer, MD rock classes. Okay, this is good. This is not quite as complicated. It gives us something to start with. The next thing we want to know is, what do these colors mean? We could click on them, but with only these few colors, it works better. We can just click on the legend up at the top of the map, and it would tell me each color and what it means. That's one way to get it. I'll also let you see another way. If I stayed with the content page, I can actually click on the name Maryland Rock Classes, and it pops up some more little icons to apply to this layer. And one of them is the legend. And so what you can see, by the way, on this map, once you go to it, once you get the link and go to it, you can play with it all you like. A lot of things are buttons. You can't mess it up. If you ever get kind of lost and not sure where you are, just reload it and it'll start back to where it was. So this is a tool which I hope you have fun with and can play with. Okay, so on the rock classes, what do we find we have? Well, let's see, if we start with the coastal plain, we see this tan color is just sediment. It's not even sedimentary rock. It's just sand, gravel, and clays, and that's all there is. And not really a hard rock. We move to the Piedmont, we find it's mostly metamorphic rock, as shown by the green. A little bit of sedimentary out here in the Frederick Valley. And you keep on going to the Blue Ridge, and it's also metamorphic rocks. And then keep on going out farther west, you're in the yellow, which is the sedimentary rocks. Now you say, well, wait, we didn't get much igneous there. We didn't. You might have noticed a little bit of red down here in parts of the Piedmont. Okay, there are our igneous rocks. We don't have very many igneous rocks that are true still igneous. We have had a lot more rocks that were igneous, but they got metamorphosed in various collisions of plate tectonics. And so we only have a few of the igneous. Still, we'll talk about those because they're also interesting. Right? So I'm going to go back out to all of Maryland. I have one thing going on here where I am. I'm going to get the lights back on. That'll happen a few more times. Don't worry about it. That's good old automatic lights. A little distracting, but okay. So now we can look at the rock classes, and what we can also see is the classes often match the provinces. So if you know where you're going in Maryland to collect rocks, you can anticipate what kind you're going to find according to what province it's in. So that can be very helpful. Okay, so here's the point where I'm going to show you some of these resources, and here is the link for the Maryland Geology for Education web map. I think Bronwyn's going to put a whole bunch of links in the chat at this point, and what you can do is drag your cursor over all of them and copy them and then paste them into some other document or whatever works for you. There'll be a bunch there and you can work with them. I hope you'll keep watching what I'm doing for now, but you'll have the links for later. Maryland Geology for Education gives you Maryland geologic maps, but if you need the entire US or even more detail for Maryland, this is the National Geologic Map Database. So you might go there, okay? We're going to talk about minerals and rocks. Obviously, we've started, keep going. Here's a good website. The GeoRockMe website is kind of a tutorial on minerals and rocks. And so it might be useful if that's something new. You can go at a slower pace than I'm doing just in a quick hour tonight. Also, I can talk about my stuff as geology, but this is also considered to be rock hounding. So rock hounding sites may be another place where you can get lots of good information on what to collect and where. There's one example, and you can always Google that. Books, some of you all have mentioned, thank you. My book, Maryland's Geology, and it's kind of a Geology 101 course that then applies it to the state. So you can read that if that will help you understand what's going on in the state. Then there's also the Roadside Geology of Maryland by John Means. It's also done very well. This kind of shows you where to go to find some of the rocks you might read about in Maryland's geology. And I appreciate Bronwyn saying I wrote the book. Well, actually what I did was I read a lot of other books from the geologists and kind of hopefully translated them into English. So I, as they say, stand on the shoulders of giants who did a lot of the research out in the field. So, okay, so now you got some resources there, which I hope you can get out of the chat. And suppose we start going out and looking for stuff. Suppose we want to find those igneous rocks, and actually this is a good batch of rocks to talk about first because they'll help us with the identification process. As I said, Maryland has had igneous rocks. We've had volcanoes in the past, but they've changed to metamorphic rocks. Still, we do have some, okay? And so what textures and compositions would we look for in igneous rocks? Okay, well, here's a set of common igneous rocks, and you can see their names underneath. You know some of these. Everybody knows granite, diorite, maybe you know gabbro, rhyolite, andesite, basalt. There's 6 different igneous rocks there. It turns out igneous rocks are among the easiest to sort out, at least on a basic level, because they fit into our texture and composition categories quite nicely. So what we have here is the way these are arranged. You see all the ones on the top are coarse grained. I can put the cursor on different minerals within them and point out white or dark places. Meanwhile, the ones on the bottom are all fine grained. There are whole places, sections where you can't really differentiate anything. Here's another sort of section in here, over in here. There are some places where you can see spots. It's quite normal for these fine grained igneous rocks to also have little crystals in them, okay? But the matrix itself, the background is all fine grained, and that's what makes them fine grained overall as we look at them. So you can sort these out into two groups, whether they're coarse or fine. And then you can also see as you look at these across from left to right, it's also, they're separated by their composition. There are more felsics on the left, which are the light colored minerals, and more mafic on the right side where it's more dark minerals. And the ones in between are intermediate. So it's a really nice, neat, logical way of arranging these rocks, and the igneous ones show that the best. So for an example, for Maryland, this is the close-up of the Ellicott City granite. Granites are coarse-grained and felsic. So you can see the grains on this one. I can definitely point out these kind of pinkish feldspar, potassium feldspar grains. A lot of the other white is other feldspars, and there's some quartz. And we have a little bit of the mafic, a little bit of the darker. But the point is, it's definitely coarse grain, and overall, it's pretty light colored. Okay? That's what makes it a granite. And so we can look at that easily and see them. If you want to collect Ellicott City granite, you're probably going to best collect pictures. You can go take pictures of most of the buildings in Ellicott City, and you'll have that. Here's another sample that was near Ellicott City. Again, you can see it's coarse and mostly light colored, so it's felsic, and but it has a few blobs of some of the rocks that came as the granite was squeezed into the rock as a liquid. It pulled a few other chunks off of the surrounding rocks, and they were floating in the magma till it cooled along with the rest of the granite. So you may find other things in it as a mixture. It kind of tells you the story of what's happened to it. Here's another granite. This is the Woodstock granite, and this is near the Woodstock quarry. This one is obviously not a close-up. It's large pieces. This is when it really begins helpful to collect pictures instead of these chunks, which you can't take home because they're too big and they're in a state park. But still, you can collect the place and take a moment and kind of remember, oh yeah, we've seen this granite as well. Close up, it would look similar to the Ellicott City. If you get out in other places, here's another rock that you'll find, which is igneous. It's called pegmatite. It's known for having very large crystals. So you notice we were looking at some that you could kind of put a pencil on or something, but in this one, all of this tan mineral is the same mineral. It's all a piece of potassium feldspar, and you can see it's much bigger than a pencil point. And then all the white stuff up in here is a big piece of quartz. So in pegmatite, you get very large grains of minerals, which makes them a neat place to see the minerals. There's more as you go look around. This is a pegmatite in Lake Roland Park. Again, the tan is the feldspar, and the gray and white is mostly quartz. I keep looking around. Here's one that's in the Gwynns Falls stream in Baltimore City. Again, the tannish stuff is the feldspar, and the lighter stuff is quartz and a few other different feldspars. Turns out these weather kind of slowly because they have big grains, and it's one of the reasons why we have rapids and falls on the Gwynns Falls, and why you have the Cascade Trail in Patapsco Valley State Park. That's because of the pegmatites. And here's a pegmatite that's squeezed its way in a crack between two rocks. The pegmatite starts here, and it's the pink feldspar and on one side and pink feldspar on the other, and quartz in the middle. Okay, it cooled slowly, and also the way that its chemistry was made it form into fairly large blobs of the same mineral. Again, here's one that you can take home with a picture, but you probably can't chip it out. So another way to collect rocks and see. Keep a collection of the cool rocks you've seen one way or another. Okay, there's our igneous rocks that we can find fairly easily. So we can move on to the next one, which our igneous might become sedimentary if they wear down. Let's talk about those. They come in two main forms. They're either clastic, made of pieces, as we've talked about before, okay? And those are classified mainly by size, or they could be a precipitate. They've been chemically deposited, and therefore they'll make a mass of crystals. So they'll be crystalline, and we look at them by composition. Let's look at the clastic ones first. Okay? The clastic ones separated by size, I'll put all of these up so you can compare them. If you have large pieces that have been stuck together, that's a conglomerate, or also could be a breccia. Conglomerates usually rounded pieces. Breccia is ones that are angular. If the pieces get worn down to being the size of sand, then we have a nice easy word. It's sandstone. Okay, sandstones will be mostly quartz because the other minerals are less resistant than quartz. And anytime you're on a beach, you'll probably find a lot of quartz in the sand, though some people, besides collecting rocks, you can collect sand because sand is different everywhere you go. And that's another kind of cool thing. And finally, if the pieces are too small to see individually, these will probably be pieces of clay. Clay is a weathering product as feldspar and some of these other rocks break down. Now the pieces all just mush together, and you can't, when you pick up a bunch of mud, you really can't see individual particles. That can make a siltstone, it may make a mudstone, or we also talk about shale. That's one that has a muddy rock that has a lot of layers, okay? But all of these are the finest grain stuff down here at the bottom. So we're getting more and more fine as we go down the list. And so here's a picture of conglomerate. We have some of this out in the Frederick Valley. You can see the big pebbles that are all stuck together to make this rock. Here's a coarse sandstone. We saw this picture earlier, but now it has small pebbles and some sand in it together. So we might just call this a sandstone, but it does have some bigger pieces in it. Sometimes the sand is really sand sized. This is out at Muddy Creek Falls. Now the pieces have gotten really small, and sometimes they get so small they're kind of hard to see, but now you can look at the whole rock together. This is showing what's called cross bedding. These slightly diagonal lines that go through this. That happens when you have sand dunes, either underwater or on land, and they blow around and give you some of these faces as the sand moves together, and another one flows the other way, and so on. So again, it starts telling you a story from the texture that you see in the rock. Meanwhile, the shales, which are the ones made of very fine grains, will be smooth and not have a whole lot of other texture. But interestingly, here, for example, this is the Wills Creek Shale. This was some mud flats when it was first deposited, and you've probably seen mud or puddles that have dried up and cracked into make mud cracks. Well, these mud cracks are actually preserved in the rock. So we had a layer here and another layer of mud on top of it, and it dried out, and another layer on top of this, and it dried out, and so on. So the rocks can begin to tell their story of where were they deposited and what happened as they got there. The shale, again, is very fine grained, not a whole lot else to see. Here's another piece of shale, and you can see over here it's very smooth and has lots of thin layers in it as a mud deposit. You can also see on this one ripple marks. You've probably seen those in sand or mud around the ocean or other places. As the currents go by, it can kind of push this stuff into little ridges. So again, we kind of see the story in the rock in addition to identifying, oh yeah, this is layer of shale, fine grain rock. This point is, picture is here to kind of to mention that the sandstones, particularly out in the valley and ridge and the plateau, are the ones that are mainly making up the ridges that are out there. The sandstone being mostly quartz, it does not wear away very easily. It's very stable. So the sandstones remain at the top of the ridges while the limestones and the shales wear away in between. And so if you're collecting at the top of a mountain somewhere, especially in Maryland, it will probably be sandstone, except we'll see some quartzite. But throughout those western provinces, that's where you would collect sandstone, is at the top, and other rocks down in the valleys. The precipitates, the other kind of sedimentary rock, the main one to know really here is limestone. It's made of the mineral calcite that we looked at earlier, the soft one that made fizz. Limestone comes in a huge number of forms, but you can tell it by testing for calcite or kind of check its hardness. One thing to know about it is the calcite, the calcium carbonate, dissolves slowly in rainwater. So it tends to wear away little by little over thousands of years and longer. And so it's one of the less resistant rocks in our climate, whereas the sandstone will usually last longer. And so the limestone may make up the valleys out west. We'll see it also when we get to metamorphic rocks. Here's an example of how limestone can weather. This was in a dry climate, but this rock was underneath a place where rock dripped off of a cliff. And you can see as the drips go down, they would then cut a little gully through the rock and run off and cut another gully here and another gully there. And you can see how this rock can get this shape from being dissolved away very slowly and get what's called fluted like this, so that it's got lots of little grooves. Limestone tends to wear away in a wet climate. Last class of rock is for metamorphic rocks. For any of you who are somewhere around north and west of Baltimore and DC, which may be a bunch of folks, you're in a Piedmont and it's mostly metamorphic rocks. So we'll take a good look at those. Just a reminder, in metamorphism, what happens is the rocks remain solid, they don't melt, but it is possible for the atoms to move around and make different minerals. And this comes about by having heat and pressure on it and fluids that may run through. This will be hot water, and it can carry along and dissolve stuff and move atoms around. So what that means is when you do it, you get new textures from what it started as, and/or you get new minerals. And since texture and mineral is the way we classify rock, this means this is a whole new rock. So that's why metamorphic rocks have their own class, because they've changed. The classification is based on texture first. I'll put both of these up so you can see them. Okay, we say they're either foliated or non-foliated. And foliated means there's layering of some sort or other, maybe different minerals, or it may break into layers. Whereas non-foliated, it's not necessarily layered. It might be layered in some ways, but it's not necessary for the classification. So we'll look at these two and how would they look like if you find them in the Piedmont. Okay, so here's a slide which looks at the four main metamorphic rocks that are foliated in yellow: slate, phyllite, schist, and gneiss. This is what you get if you start with the sedimentary rock shale, which we looked at, and you start squeezing it. You squeeze it a little and it turns into slate. And you squeeze it some more and it turns into phyllite, and some more it turns into schist, and some more it turns into gneiss. And if you kept squeezing at this point, by the way, and heating it, the next step would be it would melt and you turn into igneous. So these are our metamorphic rocks. And it's a continuous series from just a little metamorphism to a lot. And we call that low grade to high grade metamorphism. The composition, as the atoms rearrange, you get more and more mica in larger grains as you go through this series, and you start developing some feldspar. Then the other thing that happens is we're going to look at the pictures. You're going to see, you probably know, slate is a real flat rock and breaks into nice even layers. And so you have a strong tendency to do that here, but as you go to the right, it has a decreasing tendency to break in layers. Meanwhile, going the other way, the slate does not have layering of minerals, but as you go to the right, you have more and more layering of minerals. And so they're both foliated, but one breaks in layers, and the ones on the right tend to be layers of minerals. So that's the difference in the foliation. Grain sizes usually also get larger as you go to the right. Okay, so what do these look like? So you probably do know what slate looks like. Here's some slate, the peach bottom slate, which is up in northern Maryland. This quarry is not really accessible, but you may find some other slates. And if you look at the edge of a chunk of slate, you can see it does have lots and lots of fairly even layers, but not much layering of minerals. It looks all consistent. This is taking the shale, which had layers, and squeezing a little bit, and the mica beginning to form. So it gives you more distinct layers that you can split and make slate for like roofs or sidewalks or something like that. Okay, they're very convenient for that. We go to phyllite, the next metamorphic grade. This is looking edge on at a piece of phyllite. You see the layers are getting a little more uneven, may have another kind of mineral in there. Another way to see it is so what we call an outcrop, a big chunk of it. And you can see it has lots of layers tilted in this case, but they're beginning to get folded a little. They're not the nice even layers of slate. And you may have some bits of quartz or feldspar within it. That's a phyllite. You squeeze it some more and you get more and more mica, and you start having a pretty shiny rock called schist. The light colors on this are the sunlight kind of getting off of this, and that's the mica. Another thing you often find in schists are garnets. The garnets are the little round, dark grains in this. These are usually too crushed to make make it good for a ring or a gemstone, but the garnets kind of help you identify that you have schist. The schist now also has other minerals in layers. So here we're looking to edge on a piece of schist, and you can see the light layer here and a dark layer there, and here's another lighter one. And it's also beginning to get folded and twisted because getting more and more heat and pressure, they get a little more and more irregular. So as you can see, this is an Oregon Ridge. We have a lot of schist deposits in north and west of Baltimore. So this is the trail in Lake Roland Park. A lot of these are places where the rocks have been exposed because somebody cut a railroad bed through it. And so, okay, it makes it easy to see all the layering and a big outcrop. There's one and another trail where that's happened, the Torrey Brown Rail Trail. This is all schist, which accumulated as mud in shallow water in the distant 400 or 500 million years ago. And then it's been squeezed to make the schist with all of its layers. Sometimes you can really see the folding in the layers. Also, this is the Oella schist. This is on the trolley trail that goes between Banneker Park and Ellicott City. And it's kind of neat to see how the layers have varied and gotten a little twisted around, so forth. This also begins to spill over to our igneous rocks because we're heading toward Ellicott City. Here is some Ellicott City granite that has intruded. Here's another batch up there. So the rocks can be mixed. And you can see they've kind of been through the ringer. Here's one that's really been folded. The gray stuff is the schist, even with its folds, and it has some igneous intrusions of granite on the side. So they can be a mix like that, and they make really pretty rocks with different textures. Finally, keep squeezing. We're going to get to the Baltimore gneiss. It's about 1 billion years old with a B, yes. And it's been through like 4 mountain building events over that 1 billion years. So it's at the highest grade metamorphism. We get minerals in layers, but it's not breaking in layers at all because it's too well consolidated, too well squished together. We have some layers of feldspar. The light parts and the dark parts are having more mafic minerals that are mixed in. I'm going to get the light turned on. And here's another piece of the Baltimore gneiss. Again, you can see all those layers of white feldspars and quartz in there, and more mafic minerals in the darker spots. These are kind of another pretty rock because you get all the different shapes and sizes in it. And again, you might need to take pictures because they may be too big, but that'll give you a pretty background. Okay, those were the foliated metamorphic rocks. Now we should do the non-foliated ones. I'll put both of these up so we can compare them. They're classified by composition, and one is quartzite, which some people mentioned in the chat already. That's good. And the other is marble. So quartzite is what you get when you take that quartz sandstone that we kind of looked at earlier, and you metamorphose it, you squeeze it. You squeeze the sand grains so tightly together now that if you break the rock, it doesn't go around the grains, it can go right through them because the grains are just as well cemented in as the cement itself. And so it's a very physically hard rock. If you have a rock hammer, it'll kind of bounce off for a while. And it's all because the quartz is chemically inert, it's very resistant to weathering. And so this is one of our most resistant rocks that we have because of its composition as well as its squeezed together texture. Meanwhile, marble is you take that limestone that we talked about earlier and you squeeze it, okay? Now we have a metamorphic rock, okay? The composition is unchanged. It's still made of the calcite because that's the main thing that was there. But now the crystals have usually gotten larger. And if there were any fossils in the limestone to start with, they're destroyed because we've rearranged the atoms. And we'll see pictures, okay? So if you're looking for quartzite in our area, one kind you might see is this one, the setter's quartzite. It's a little unusual in that it actually does have layers, but that actually tells us more about it. The setter's was layers of sand and then layers of mud and more sand and more mud. So when you metamorphose those layers, the mud turned into micas. And here is a view of a piece of flagstone in a building in Patapsco Valley State Park, one of the park overlooks places. Because of the layers, you can break it into nice flat pieces. And what you're seeing mostly is the shiny mica that's on here. And the quartzite would really be kind of on the edge, which we can see in other pieces. In the process, it also often makes tourmaline. That's the black minerals that you see as well. So it's a very attractive quartzite, but it's because of its the way it breaks in layers. And you may see this as flagstone, or you may see it on a building. It's fairly common for that use, kind of an unusual quartzite. Okay. Another quartzite, a little more standard, is the Weaverton quartzite. This is the one that's out in the Blue Ridge, and it is the one that's responsible for the high points of the Blue Ridge because it just doesn't wear away. If you look at it in detail, we can see again some of those diagonal lines, which were the cross beds we saw in the sandstone, but now it's gotten squeezed enough that it's turned into quartzite. This one probably had some iron in it. That makes it a little bit purple. So you can see this at Washington Monument State Park. Okay? But if you also go to any of the high spots on the Blue Ridge, either Catoctin Mountain, which is what this is, or South Mountain, you can find the quartzite, the Weaverton quartzite. It makes up the rocks on the top. And that's why those spots are high, because the whole band of quartzite that goes all through here, this is Wolf Rock up in Catoctin Mountain Park, that stays up behind while the valleys wear away. And so this is Catoctin Mountain. If you go to South Mountain, you can hike up to Annapolis Rock. Here again is the Weaverton quartzite, and those quartzites are what make up the ridges. Okay, this South Mountain heads on down toward the Potomac on that direction. That's where you find the quartzite, is up on those metamorphic rocks. The marbles you can find in different places. Here's one pretty easy to find if you're in the Baltimore area, up behind what was the Hunt Valley Mall, now the Hunt Valley shopping centers that are there. Tends to be light colored like the calcite, but marbles often end up having some bands, color bands in them due to different compositions. And so they're there. You also may find sometimes ones that have lots and lots of stripes in them like these. This is kind of like the Setter's quartzite in it. It was a layer of marble and then a layer of mud and then a layer of marble and then a layer of mud, back and forth. These are kind of attractive and interesting. They're kind of distinctive. Whenever you find this, this is the Cockeysville marble, and it's come out of the big quarry in Cockeysville. That also kind of is a good point to mention that, remember, this marble is calcite, and we talked about how limestone wears away in rainwater. So wherever you find this marble, and we find a good bit of it north of Baltimore, it tends to make a valley because it has worn away, and while the schists that are around it doesn't wear away as fast. So this is the rock that underlines the Green Spring Valley, the Cockeysville Valley, Lutherville, Timonium, on around to the Worthington Valley and so forth, all because the marble is there. And it often can be a little bit hard to collect, to be honest, because it's way down deep in the soil and wearing away, but you still may see it because a lot of it gets quarried. And in fact, you may find a lot of the marble in chunks like this because it is a common crushed stone in our area. You may find it as white, it may be gray, it may be crystalline with some little brown mica in it, so forth. This is kind of an easy rock to collect around here because anybody putting in a driveway or a road, they probably put in a bunch of this first. Okay? So you might pick up a bunch of that. Also in this picture, some other pieces of quartzite. Here you can kind of see the texture in this one that's original, but sometimes it gets so squeezed together, it gets pretty smooth and almost is just a solid chunk of quartz. Sometimes it can be red. Rocks can come in a lot of different colors depending on what's added to them. And this is also kind of, besides marble being a very common rock to pick up somewhere because it's used as crushed stone, the other common rock will be quartz, pebbles, because they're the thing that's left behind when everything else is falling apart. So if I get students to pick up rocks in their neighborhood or something, a lot of stuff that comes in will be marble or quartz. And okay, that's instructive as what you have. It shows us what you get kind of when things are wearing away or they can be man-made. It's always a little bit of a problem in an urban area. You're never quite sure what rock has been carried in and what's natural. Okay. Finishing up on some other metamorphic rocks we find around here. There were some volcanoes and island arcs that were much like the Aleutians that got pushed onto Maryland in the past. Those rocks then got metamorphosed. They were originally basalt or gabbro as igneous rocks with a lot of mafic minerals. Now they make a rock called Amphibolite. Okay. If you look on the geologic map, you'll see them listed as the Baltimore Mafic Complex. They look like that. They're black, okay, because they are very, very mafic. You can find them in a lot of the, especially the lower parts of Patapsco Valley State Park. That's what you're looking at when you see the black rocks. Another one that you find around here is serpentinite. It comes from pieces of the ocean crust or even the mantle getting pushed up on the land and then getting changed by hot water and other things that go through them. This is really less heat and pressure than they form. It's not usually common, but actually it is found in several places in the Maryland Piedmont. Soldier's Delight is a really good example. It's often greenish when it's fresh, but it weathers to brown. You may know it's been mined for chromite, and it really lacks the nutrients needed for most plants because of where this rock came from, and the plants are adjusted to rocks on land, not ones from the ocean or the mantle. And so they get kind of poisoned. This is where you get serpentine barrens. And so you might find the Bear Hills in Baltimore. This is also serpentinite. So this is another metamorphic rock. However, to be honest, it's not very pretty usually. It's kind of a green and brown. And there it is, but it's nice to know what it is and what it tells you about the place that it is. And a third metamorphic rock is in the past, continents have split apart, and we've had a huge bunch of volcanoes in Maryland. They put out a lot of basalt, which is like the lava that comes out of Hawaii. That gets metamorphosed into metabasalt or greenstone because it looks kind of green. Also, in a few places in the Blue Ridge, you can also find places where these volcanoes put out volcanic ash, and it's metamorphosed into the metamorphic rock phyllite. The metabasalt is the one that we can really see the best because it covers a lot of places. Here's a big chunk of metabasalt, and you can see from there, a good place to see it is Cunningham Falls State Park. There's lots of the metabasalt there. You also see it in some of the road cuts along Interstate 70, but of course, don't stop on Interstate 70 and collect rocks. But so this is the kind of stuff you can see, and you see we've covered a lot of variety out there in Maryland of all kinds of rocks, and I hope this is helping you kind of figure out what they might look like. Now, if we go back to the coastal plain, it turns out, remember, they were mostly sediments, sand, gravel, clay, haven't been turned into rocks. Not a great place for rock collecting. However, as you all know from Calvert Cliffs, can be a good place for fossil collecting because and the other rocks in the coastal plain, the other sediments, they can preserve the fossils instead of destroying them. So you may look for fossils there. Sometimes the sediments do get cemented, especially as water goes through and carries iron and it deposits it out kind of like rust. So you can find conglomerate areas in the coastal plain rocks. This is at Elk Neck State Park. Okay, it's the pebbles have been cemented together with iron. Here is a bunch of sand that's been cemented by iron. You can kind of see that purple color is the hematite, the iron oxide mineral that's in it. And here's another of that kind of thing, which is sand and kind of purple in some places, but it also has some pieces to make it kind of a iron cemented conglomerate. And it's either kind of the purpley iron oxide, or it may be the rusty brown iron oxide. But those are the kind of rocks that you'll see in the coastal plain. Okay, so there's our bunch of rocks, and I'll finish up by talking about what you might do to collect and some tips on that. I found that brown paper lunch bags are a great thing to take when you're going to go collecting because you can put the samples in it, you can write on it as to what it was and when you collected it. And so when you put it in your basement and don't get around to picking it up again for a while, you can still remember what it was, okay? And so that can be a simple, useful item. You really can see a lot more if you have some kind of magnifying lens. You can see the sand grains and stuff, or you can say, oh wait, there aren't any sand grains, so it must be even more fine grained than that. Some kind of magnifier is a recommended tool. And if you want to be able to tell the calcite, the limestones from other things, you might want to get a dropper bottle with a good top on it. And you can get hydrochloric acid. You can buy muriatic acid at Home Depot or somewhere. But unfortunately, it's a whole gallon, so you can use it for a long time. But you can use it to test for calcite or dolomite. When you get your collection home, now what are you gonna do with it? You want to be able to remember where it came from, what it is, ways to keep track of your collection. You can put them in small boxes with a paper label. That's one way that works. You can add a small patch of white paint, and once it dries, you can write a number on it. Or another way to use a number is put it on a small piece of paper. Your computer printer will probably make small ones, and paste it on. Okay, that's another way to do it. Now, of course, all they have is a number then, so you have to be sure to make a catalog either on your computer or file card, some way, so you remember which number is what. Okay, that's a piece of this one, and then don't lose the catalog. If you have a big enough sample, you could even paste on a label that has some more information on it. Depends on the size of the sample. If you need more ideas, hey, Google them. Look, search around for ways to label rock collections. And among the items in the chat is this URL for a long article on labeling. This is meant mostly for minerals. And I might, just so everybody hears about it, mindat.org is a major mineral website for all kinds of information on minerals. So this part of it will show you about labeling. And then here's another one, which is mainly for labeling rocks. Okay, so either one of those might help you with some ideas. So I hope you enjoy your collecting, whether it's real rocks or pictures, whatever works. Okay, our Earth is really amazing and really awesome, and all kinds of cool stuff out there. So I hope this encourages people to get out and see what's going on, and maybe you'll bring home something interesting to remember. And it can be rocks, can be pictures, can be memories, and a whole lot of things like that. So I'm going to stop, and we can also start, we can look at questions, and Bronwyn can tell me some, or I can also look at the chat. So let me know what questions you have.
That was wonderful, Martin. Let me.
Sorry, it's kind of a deluge of information all at once, but hopefully you got a little something that you can remember.
No, my mind is on fire, and that's why I hate sometimes these being in the evening, because now I'm so jazzed. I want to go out and look for rocks outside. So, but I have to wait for them till tomorrow, because I don't think collecting rocks at night, you would recommend that. I don't know, maybe you do, maybe you do. Let's see. If you have a question for Martin, you can raise your hand on in the app, and I will call on you, or you can put it in the chat box. Jeff asks, how much should you dilute the muriatic acid to be safe to carry, but it still gets the fizz? Yeah.
Okay. I have to look at exactly what it's on the bottle of the one you get, but you can easily dilute. I would say 3 to 1. Or 5 to 1, and also you can experiment. In other words, dilute it so where you feel like it's gotten diluted and it be pretty safe. Try it on some rocks that are limestone and see if you get a decent fizz that shows you something. If not, make it stronger, or if you find, hey, wait, I don't need that, you can make it more dilute. But it depends on what you're starting with. But yes, diluting it is a good idea. You can try, 3 to 1 or 5 to 1 to start and see how it goes.
All right, Bailey has their hand up. Why don't you go ahead, Bailey?
Yes, so I found some rocks that look kind of like your iron cemented conglomerate picture. I found them at Douglas Point and Perch State Park, kind of in the coastal plain area, but they've been like hollow. They've been like tubes or connected chambers. And the best guess I had looking online was fulgurites, but I was wondering if there was another explanation what they might be.
Well, yeah, you find the ones with tubes and so forth are really probably worm burrows where worms have gone through and they've kind of made a hole, and that's made some, either helped make some cement around the outside. And obviously it's easier to have worms than to have lightning hit something. So you will find those kind of rocks. And also the way the water moves through the sediments can be very, very unusual sometimes. So you get very unusual shaped rocks out of those iron cemented rocks. They can be just kind of a bumpy boulder. They can be look like some of the tubes you're talking about. And so it's very variable because of the way the water is moved through.
Thank you.
All right, Stuart wants to know, where can they find Patuxent River stones? And that is the gem. It's called the Maryland State Gemstone, but I'm not sure if it's a gemstone or not.
Yeah, it's kind of an odd rock, and actually it's not exactly Patuxent River. We're really not completely sure where this comes from or how it formed. It may have come out of the setter's quartzite, that it got kind of dissolved and then reformed almost as a gel that's then got solid. I've seen some rocks close to it in kind of near the McKeldin State Park, but again, don't collect those. I don't know of a good spot. It'll probably take some more research to find where people have found it. It's not very common. So if you have some, keep it, but you might want to look for something else because this one is so hard to find.
Jay also mentions that calcite is usually fluorescent under short wave. So do you think, and some other folks talked about the fluorescence. Do you want to talk a little bit about that? Is that a way that you ID or look at rocks?
Yes, that can be a cool way of seeing the rocks. It's really interesting to be able to turn off the lights and turn on fluorescent lights, and now your rocks all glow in that. And actually, Brian, when you were talking about we can't collect at night, well, actually you can collect at night if you go out with your fluorescent light, and you may find some neat stuff. Calcite can glow red or greens and so forth. So that is another thing you can do is if you collect some calcite, you can check it under fluorescent light and see is it glowing in some way.
All right. Anne just wants to know what that color wheel behind you is that she's been looking at.
Okay, it's actually an exercise on the interior of the Earth, and you get a pie sort of slice, and these are a whole bunch of those pie slices put together, but they weren't all colored by the same student, so they don't all look the same. This is just from an exercise in which students are learning what is in the interior of the Earth.
And more about you might have mentioned this, why do the rocks fluoresce?
Fluorescence is usually is a physics phenomenon where the energy is coming in at an ultraviolet wavelength. Okay, it knocks electrons up and they have more energy for a bit, and then as they fall back to their normal state, they give off the energy that came in, but now they give it off in visible light. And so what it's done is change the energy coming in from ultraviolet to visible light, and now you can see it, and that's what causes fluorescence in general.
George, did you have a question?
Yeah, I wanted to make a statement. What Martin was saying about labeling, that is so very important. With the fossil collection, we get donations every once in a while, and sometimes it's just a bag or several boxes of stuff with fossils, but nobody's labeled them. We can guess at what the fossils are, but if we don't know where they're from, it really makes it a problem because they're not worth any value scientifically. We can give them away as donations, to kids and stuff, but we really can't use them in the collection.
Yes, thanks, George. You're right. Any donations that we might get end up being a lot better if, get the light back on again. A lot better if they've been labeled in some way, because that way we know where they came from.
Yes.
Sometimes we even know when they were collected and so forth. I'm working through the cataloging stuff we have from the past right now, but it's also finding various mines where minerals came from. Where is that location? What's the rock under there? So yes, as much as you can keep track of what you did, that's great. And I do find I use those brown paper bags a lot because otherwise I'll forget which piece is which.
Yeah, it's a good habit to get into, for the other collectors that are here, they don't do it already.
Yep.
Thanks, George. Any other questions for our rock star Martin for tonight on National Collect Rocks Day with all of our rock stars here with us tonight?
I appreciate your attention. I know it's a lot of information, quick, and thank you for your attention through all that.
Yeah, it is a lot of information, but it's wonderful. And we're all going to go out and read the rocks more closely. You've given us some vocabulary, a way to look at rocks with new eyes. So thank you for that. Thank you always for sharing your time, your knowledge, and your expertise with us. Everybody here is smarter for it. And now you take that knowledge and share it with other folks. And come back and learn some more with us. Remember, next week we're learning all about rodents. So come back and learn about rodents, everything you wanted to know, but we're afraid to ask. Thank you, Martin. Everybody stay safe and stay curious.
Thanks for your compliments. Have a good week.
Thanks, Martin. Hopefully we'll see you soon down in the basement.
Thanks.
Yeah, Lori, did you have something to say?
Nope, just thanks.
Oh, you're welcome.